Okay. So we have two methods for doing this. The first one is a little bit more intuitive and a little bit simpler and more efficient. However, it doesn't always work. So it's somewhat similar to like solving quadratics, right? Factoring is the most efficient way to solve a quadratic equation, but it only works if we can factor. So we have other methods to use in case we can't factor. So we're going to use the same kind of idea here. The first way we have for solving we should define exponential equations. So an exponential equation well, it has to be an equation, of course, so it has to have an equal sign. So we're solving for x, and our variable is in the exponent. So that's how we know that it's an exponential equation, because they can often look similar. So I could have an equation like 4x to the third equals 7. That is not an exponential equation because my variable is the base, not the exponent. And so to solve this equation, we would just divide both sides by 4 and then take the cube root of both sides, right? So we use radicals to undo exponents when the exponents are constants. But if I have like 4 times 3 to the x equals 7, I can't like take the xth root of both sides to solve for x because I don't know what the xth root of a number is, even if the number doesn't have a variable in it. So these are the types of equations that we're solving today. So where we have the variable in the exponent, so we can't use a radical to undo the exponent. So the first method we will use to solve these is called relating the bases. So solving by relating bases. And I should tell you, we will ask on the test, we'll tell you if we want you to solve by relating bases. So there's, like I said, there's two methods, and the second method will always work, but we will ask you to actually show us that you know how to solve by relating bases, because it's an important skill. So this relies on the idea that if you have two expressions that are equal to one another, and they are both exponential expressions with the same base, well, if those two numbers are equal, then, and their bases are equal, then their exponents have to be equal as well, right? There's only one number I can raise 2 to in order to get 2 to the 5th, and that is 5. So that means that if these two things are equal to each other, all the components have to be equal, so x has to be 5. That's the only option here. And so if we can get both sides of the equation to be single exponential expressions that have the same base, then we can conclude that the exponents are also the same. So we can conclude that x equals 5. And there's not like a mathematical operation I did on both sides to conclude that. I just kind of use logic to say, okay, these are equivalent and therefore the exponents are equivalent. What's up?
Can you do the same thing if you can get it to two equal equations? Like if you had 2x equals 2 to the 5th plus 4, and then you just move part of it over?
2x
just trying to think
equals, do you mean like this?
No, with the x and the exponent. I was trying to think of a way to make it so that the equations are equal so that it's the same thing. Would that just be that you'd have to get rid of everything else so that you have just the exponents?
Yeah, so in this case, we wouldn't be able to solve using relating bases because I can't make both sides exponential expressions. So even though I could write the 4 as 2 squared, 2 to the 5th plus 2 squared can't be combined as 2 to a single power. So I have to be able to write both sides as a base raised to a power without anything else going on outside. So because of that addition, I can't solve using relating the bases.
A way to make it so it's like 2x plus 2 equals 2 to the 5th plus 2.
Yes.
It's the same equation on both both sides, can you make it so that it's equal, or would it be better to just get rid of
So
everything
do you
else?
mean like, I think I see what you're saying. Like if we could make it like this.
Yeah. Or would it be easier to just get rid of everything besides the exponents?
Well, so I could do, so that second one I could solve, like I could subtract 2 from both sides, and then that would give me 2 to the x equals 2 to the 5th. However, these two equations aren't equivalent because to get plus 2 on the right side, I would have to subtract 2 from the left. So there's no way to manipulate that first one so that I can just isolate the radicals on both sides.
With the first one, I've just been saying the first thing that came to mind, trying to get to the second one.
Right. So yes, ideally we're going to get something like this, and we might have to manipulate both sides of the equation to get there. So let's look at a few more and how we're going to get there, and when we can and when we can't. So that first one, we could never get to that point where both sides are just an exponential expression because of that addition. So no matter what I do with that 4, I can move it back and forth, I can separate it into 3 plus 1 or whatever, but there's no way I'm ever going to get just an exponential expression on both sides, which is our goal. So, but let's do some, because you've got the right idea, let's do some where we actually can make that happen. So our first step is to rewrite both sides as a single exponential expression with the same base. So in other words, like a to the something equals a to the something else. There can't be anything else going on outside of the exponential expression. It can't be like a number times a to the n equals a to the m. The entire left side has to be a raised to some power, and the entire right side has to be a raised to some power, whatever a happens to be. So that's why there's limitations to using this method, is that not all equations can be written that way. But if we can, then we can relate the bases and say that the exponents have to be equal to one another. So for example, if I had 2 to the 3x minus 7 equals 32. So the general approach I take when trying to relate the bases, so trying to do that first step where I write both sides as a single exponential expression, is I just do the prime factorization of any numbers that aren't in the exponent. So in this case, 2 and 32 are the numbers I'm looking at. If you do the prime factorization of 32, you see that it's just 5 factors of 2. And so we can rewrite 32 as 2 to the 5th. And again, that's just the prime factorization of 32. I just wrote it in exponential form instead of writing 2 times 2 times 2 times 2 times 2. I don't know if I said 5 2s, but you get the point. So now we have 2 raised to a power on the left and 2 raised to a power on the right. Nothing else going on outside those expressions. And so we can say that in order for this to be true, the exponent on the left and the exponent on the right have to be the same, which means we can say that 3x minus 7 has to be equal to 5 in order to make that true. And so now I have a linear equation that I can solve. So our second step is to set the exponents equal to one another. And then we solve. So 3x equals 12, and x equals 4. And unlike the logarithmic equations that we did yesterday, we don't have to check for extraneous solutions because remember the domain of an exponential function is all real numbers, which means no matter what I get for x, I'll be able to plug it back in and it'll work just fine. So an exponential expression is never undefined for any value of x. So we don't have to worry about that in this case. The main thing is just that step where we rewrite both sides is sort of the trickiest part of this. Once that's done, we're just solving a linear or quadratic equation. So let's do a couple more so we can see kind of the different ways this can come up. Let's solve eight to the x equals 64 over 4 to the 2x. So again, I always start with prime factorization. Theoretically, there could be some of these where you could write with a base that's not prime, like use a base of like 4 instead of a base of 2. However, for instance, in this one, I could write the entire right side with a base of 4, but the left side, I can't write 8 with a base of 4. So your best bet is just to use the prime factorization because you're breaking everything down into its smallest pieces. And so once you've broken everything down to its smallest pieces, if they don't have the same base, you know that there's no way you can get the same base. So I'm going to write 8 as 2 times 2 times 2, so 2 to the third. So I have 2 to the third raised to the x, and then 64 is 2 to the 6th. And again, just do your prime factorization to figure this out. If you don't know off the top of your head that 64 is 2 to the 6th, just divide 64 by 2 and then by 2 again. So just like you can even do a factor tree like we did with prime factorization. So this is 2 to the 6th, and then 4 is 2 squared. And now we have to use our exponent rules. So remember that raising an exponential expression to another exponent, we just multiply the exponents. So on the left side, we have 2 to the 3x. And on the right side, we have 2 to the 6th over 2 to the 4x. And as you get more comfortable with these, you can jump right to that step. Like if you don't write 2 to the third raised to the x, that's fine. If you know it's going to be 3x, you can just write that. And then what do we do when we divide exponential expressions with the same base? What do we do with our exponents? We subtract them, right? And so we have 2 to the 3x is equal to 2 to the 6 minus 4x. And I can't set my exponents equal to one another until I get to that point. So the step before it was all well and good because everybody had a base of 2, but both sides were not just an exponential expression, 2 raised to some power, right? I had that division on the right side. So we have to take this step to get both sides so that you have a single base, which is the same, raised to a single exponent. And so then we can say that 3x is equal to 6 minus 4x. So setting those exponents equal to one another, and then just solving that linear equation. So 7x equals 6, and x equals 6/7. Does this make sense? Okay, let's do a couple more of the kind of trickier ones. So where it gets a little bit tricky is when we have to remember all our exponent rules involving like negative exponents and radicals and things like that. So let's do one of each of those. So suppose I want to solve one over 27 to the x equals 9 to the x plus 1. So I'm going to start with just working with the number 27 as far as prime factorization, and just keep that in the denominator at first. So 27 is 3 to the third. So I have 1 over 3 to the third to the x power. And then 9 is 3 squared. So 3 squared to the x plus 1. And then how do we take the reciprocal of an exponential expression? Yeah, we use a negative exponent, right? So if I want to flip that 1 over 3 to the third, so it's 3 to the third over 1, I'm just going to put a negative exponent on that 3. So this is 3 to the negative third to the x power. And then when you have addition or subtraction in your exponent, there's no parentheses around that x plus 1 because the whole thing is in superscript and that groups it for us. Like the fact that it's all in the exponent tells us that that whole thing is like one factor. But when we multiply it by 2, then all of a sudden we have to put parentheses around the x plus 1 because we don't want 2 times x plus 1. We want 2 times x plus 1, so quantity x plus 1. So we're going to write this as 3 to the 2 times x plus 1. And that's true anytime you have addition or subtraction in the exponent. There's assumed parentheses there because the placement of that in the exponent does the grouping for you. If at any point you bring that out of the exponent, then you have to do the grouping with parentheses. So even if you're not multiplying it by something in the exponent. So then on the left, I'm going to do negative 3 times x to get a single exponent there. So we have 3 to the negative 3x equals 3 to the 2x plus 2. I just distributed in that exponent, which I could have done after I set them equal to each other as well. And then now we have our bases are the same, single exponent on each, nothing else going on either side. And so negative 3x equals 2x plus 2. So negative 5x equals 2, and x equals negative 2/5. Any questions on that one? Okay, so last one. Let's do maybe not the last one. Maybe we'll do 2 more. B times b to the x plus 5 equals 1 over the square root of b to the third. So one cool thing about relating the bases is I don't even have to know what the base is in order to solve the equation. If I can get both sides to be an exponential expression with a base of b, I can set the exponents equal to each other, and it didn't really matter what b was. So again, we have to make use of our exponent rules. On the left side, when I multiply exponential expressions with the same base, we add the exponents. So remember that if there's just one factor of b that's the same as b to the first, so this is going to be b to the 1 plus x plus 6. And then on the right side, again, I'm going to start with just, I'm sorry, 5. Yeah. So I'm going to work with just the denominator first, and then once I have the denominator written as b to some power, then I'll change the sign to flip it. So remember that rule that the nth root of x to the m is equal to x to the m over n. So radicals give us fractional exponents. So this is the same as 1 over b to the 3 halves, because that's the square root, which has index 2, which is the same as raising it to the 1/2 power. And so now we've got b to the x plus 6, just combining like terms there, And then I'm going to flip that right side by changing the sign on my exponent. So that's b to the negative 3/2. And now we have a single exponential expression on both sides. And so we'll set our exponents equal to one another. So x plus 6 equals negative 3/2. And we'll clear fractions. So 2x plus 12 equals negative 3, which means 2x equals negative 15. And x equals negative 15/2. This is fun, huh? Okay, last one. So 4 to the x times 2 to the x minus 2 equals 2 to the x squared. So again, to relate bases, I'm going to do prime factorization of all the bases of those exponential expressions. So 4 is 2 squared. So I can write this as 2 to the 2x. You can do that in 2 steps if you want. You can write the 4 as 2 squared and then multiply the exponents. But I'm happy for you to just go straight to 2x if you're comfortable with it. And then times 2 to the x minus 2 equals 2 to the x squared. Be careful when you have like an x squared in the exponent. So we have an exponential expression in the exponent. So just be careful that you don't get mixed up about what the exponent actually is. So here the exponent is x squared. That's not the same as 2 to the 2x or 2 squared to the x or anything like that. We just want to leave that exponent alone. And so then we'll add exponents on the left. So we have 2 to the 3x minus 2 equals 2 to the x squared. And now we can set our exponents equal to one another. So 3x minus 2 equals x squared. What type of equation is this? Quadratic. So I want to get a 0 on one side because there's an x squared. I'm going to get a 0 on the left side because I like to keep my x squared positive. So I'll subtract 3x from both sides and add 2 to both sides. So x squared minus 3x plus 2 equals 0. And then we'll factor. So x minus 2 times x minus 1 equals 0, which gives me x equals 2 and 1. And again, we're not going to have any extraneous solutions because it's an exponential, not a logarithmic equation. And so we are done. You guys feel good about relating bases? So let's talk about what to do when you can't relate bases. So we have, suppose something like 4 times 3 to the x equals 3 to the x. Well, let's make it kind of simple right now. Do 9 to the 3rd. So here, if I look at this initially, I'm like, oh, well, I can write 9 as 3 to some power, right? So I could write this as 4 times 3 to the x equals 3 to the 6th, right? Because 9 is 3 squared and you multiply the exponents. But then I'm kind of like dead in the water because 4 can't be written with a base of 3. And so even though I have the same base, the left side is not a single exponential expression. It's something times an exponential expression. And so there's no way to relate the bases here. And so I have to use a different method. So to solve So if we can't relate bases, the first thing we're going to do is isolate one exponential expression on one side of the equation. So what that means is if you can get only one side of the equation to be an exponential expression, you want to make that happen. Sometimes we won't be able to get just one exponential expression, but notice that on the right side, there is a single exponential expression with nothing else going on. So I've isolated one exponential expression on one side of the equation, even though there happens to be one over on the left side also. So our goal in the first step is if there's only one exponential expression, we want to get it alone. If there's more than one, we're going to get one of them alone on one side of the equation. So in this case, I mean, there's actually a couple ways to do this. I could divide both sides by 3 to the x and write the left side as 3 to some power, but I'm not sure that that would occur to everybody, and so we're just going to pretend it didn't occur to us and see what to do if we don't do that. Because if that was 2 to the x on the left side, we wouldn't be able to do that. We wouldn't be able to just write the right side as 3 to some power. So we're just going to leave them on both sides. So we've done the first step because the right side is a single exponential expression. So the next thing we're going to do is take the natural log of both sides. As convention, we always use the natural log. So using the logarithm here, we're not using so much because it's the inverse of a certain exponential expression, in which case we would have to use like log base 3 here because it's the inverse of the exponential function with base 3. The main reason that we use the logarithms to solve these equations is because of the rule that log base a of x to the n is equal to n times, doesn't look like an equal sign, log base a of x. So we can bring, if we take the log of both sides, it's going to allow us to bring our exponents down to as coefficients, and then we're just dealing with multiplication, which we've dealt with in equations a ton of times, right? So the problem with exponential equations is that variable in the exponent and how to get it alone. Taking the logarithm of both sides allows us to make it a multiplication problem instead of an exponential problem. So if I take the log of both sides, so
to take the natural log?
Yes. We always use natural log just as a convention. And I mean, in reality, it doesn't matter what logarithm you use. Any base will allow you to bring that exponent down using that rule. But like I said, it's just convention to use natural log. So, and notice that we're taking the logarithm of the entire left side, so the entire left side in parentheses. You can't do like logarithm of 4 times logarithm of 3 to the x or anything like that. It's the entire left side in parentheses as your input, and then entire right side 3 to the 6th. What is 3 to the 6th? Is it worth writing that as a number, or is it really big? Maybe you have a calculator handy. It's like, I mean, it's 81 times 81. It's a big number. 6,400. It's going to be, I think, in like the 7,000s.
So it's 81 times 81.
Uh-huh.
6,500.
Oh, I'm sorry. It's 27 times 27. My bad. 729? That's not too bad. So this is the natural log of 729. Just so you can see that like there's nothing special about the fact that that's an exponential expression, because there's no variable in that 3 to the 6th. It's just a number. And then on the left side, I'm trying to solve for x. So I'm going to expand that logarithmic expression using my log rules. So because there's a product in the input, I can write that as the natural log of 4 plus the natural log of 3 to the x. And now the key to all of this is that the natural log of a number is just a constant. So like when we see natural log of 729 and we see natural log of 4, those look more complex than numbers we usually see in equations, but they work the same way. They are just numbers. There is no way to separate like the natural log from 729. That whole thing is a single value. So trying to like look at, it's not multiplication, like it's not natural log times 729. The natural log is an operation that we're doing to the number 729 to create a new value. So it's kind of like the square root. If you have the square root of 3, you can't in any way write it like that, right? You can't separate the square root from the 3 because the square root is an operation, not like a value. The same is true with logarithms. So once you have log of 729, treat that whole thing as one number. So if I want to get my variable by itself, I'm going to move the natural log of 4 over to the right side using subtraction, because that's getting the term that contains my variable by itself. So natural log of 3 to the x is equal to the natural log of 729 minus the natural log of 4. Here you sort of have a choice. Here we have subtraction between two logarithms, so I could, if I wanted to, use my log rules and write that as the natural log of 729 over 4. It doesn't really do much for me other than make it one logarithm instead of 2. So it's totally up to you. I couldn't care less if you keep it as subtraction or if you write it as the natural log of two things being divided. So now I'm solving for x. I'm going to use my log rule to bring that x down as the coefficient. So this is x times the natural log of 3 and then the last thing to do is just isolate x. So I'm going to divide both sides by the natural log of 3. So x equals the natural log of 729 minus the natural log of 4 all over the natural log of 3. It's not necessarily pretty, but I've isolated my variable, and on the right side is just a constant. So this would be the exact answer. In my math lab, they will have you give a rounded answer, but they specifically say, like, don't round until the very last step. So what you don't want to do is, like, up here, or even right here, be like, oh, the natural log of 3 is some decimal approximation, and put that into your equation, and take the natural log of 729 and round that, and take the natural log of 4 and round that, and then solve for x. right? You want to get x by itself in terms of the exact solution, and then if you want a rounded answer, you'll plug natural log of 729 minus natural log of 4 divided by natural log of 3 in your calculator and round that final answer. It's really frustrating when you round too soon and then you're off by like 1/1000th or something like that, and my math lab keeps marking it wrong because it's off by such a small amount. On tests, I'll typically just ask for the exact answer, which means leaving it in terms of the natural log, not plugging it into your calculator. So the last step of this whole process is just solving for x. So these can look really complex because of all that natural log business going on. However, if you can keep in mind that the natural log of a number is just a number and treat that as a single value just like you would any other number, like this equation, like at this point, whoops, not at that point. Like at this point is just like some number times x equals like some number minus some other number, right? And that looks pretty simple. The equation is exactly the same. It's just that the natural log of a number looks a little bit more complex than just the number 4. Does that make sense? So let's do a few more. How about so 2 times 5 to the 5x plus 1 equals 13. So the first step, remember, is to isolate one exponential expression on one side of the equation. In this case, there's only one exponential expression in the equation. It is right here, which means I need to subtract the 1 and divide by the 2 in order to isolate it. So we have 2 times 5 to the 5x equals 12. And that step right there is really important because although we could take the natural log at this point when there's multiplication on the left, if you take the natural log with addition on one side, there's going to be no way to get your exponent down because we have no way, if you have the natural log of 2 times 5 to the 5x plus 1, there is no way to separate these two terms. I can't do that today. There it is. Because we don't have a rule for when we have addition inside the input of a natural log, right? The only rule we have involving addition is when we have addition between two natural logs. So bringing that 1 over is essential for solving this equation. If you don't do it, it's actually impossible to solve the equation correctly. So I'll also divide by 2 just to get rid of that multiplication as well. So we have 5 to the 5x equals 6. So I've gotten that 5 to the 5x by itself on one side of the equation. So now I'm ready to take the logarithm. So we'll take the natural log of 5 to the 5x. And that's equal to the natural log of 6. So now I will bring my 5x down as the coefficient. So 5x times the natural log of 5 equals the natural log of 6. And then the last step is just to isolate the x. So you want to just divide by everything x is being multiplied by. In this case, we are multiplying by a factor of 5 and also by the natural log of 5. You can divide by both of them at the same time. So x equals the natural log of 6 over 5 times the natural log of 5. And keep in mind that that can't be simplified. So just like we said over here on the right that we have no rule for doing anything with the natural log if there's addition in the input, we also don't have any rule for simplifying the two natural logs that are being divided. We do have a rule if there's division in the input of the natural log, but we don't have a rule if there is division between two logarithms. And so we can't do anything to simplify that fraction. Again, you can't cancel off the natural logs because it's not multiplication. It's not natural log times 6, right? The natural log of 6, this whole thing is one number. This whole thing is another number. So there's no way to simplify that fraction. Any questions so far? Is this making like a little sense? Let's do one more before we go. We should see one with addition. Let's see, how about let's solve 2 to the x plus 1 equals 5 to the 2x. So remember, our first step is to isolate one exponential expression on one side. In this case, we've isolated both exponential expressions by themselves on one side, on either side of the equation. So that step is done. We'll take the natural log of both sides. So natural log of 2 to the x plus 1 equals the natural log of 5 to the 2x. So we're going to use our log rule to bring the exponent down as our coefficient. Now remember that x plus 1, because it's in superscript, it's grouping the x plus 1. When I bring it down, I need parentheses to do that grouping. So this is x plus 1 times the natural log of 2 equals 2x times the natural log, whoa, I don't want parentheses there, times the natural log of 5. And I didn't put the 2x in parentheses because it's multiplication, not addition or subtraction. So I don't need to group that. Now, this is just a linear equation. So like I said, it looks a little more complex, but it's really just x plus 1 times a number equals x times some other number. So I'm going to distribute the natural log of 2. So it would be sort of like I had x plus 1 times 7 equals x times 8 or something like that. We have x plus 1 times a number equals x times some other number. So we're going to distribute that natural log of 2, which gives me x times the natural log of 2 plus the natural log of 2 equals, I'm going to write this as x times 2 natural log of 5. All I did was change the order of the 2 and the x so that it looks like x times a single number. So 2 times the natural log of 5 is a single number. And then I want to get all terms that contain my variable on one side using addition and subtraction. So I will subtract x times the natural log of 2 from both sides. So we have the natural log of 2 equals x times 2 natural log of 5 minus x times the natural log of 2. Again, those natural logs are just constants. They're just numbers. And so in order to get x by itself, I'm going to need to factor an x out. So I have a single factor of x on the right. So natural log of 2 equals x times 2 natural log of 5 minus natural log of 2. Like I said before, what's in the parentheses there, we could condense using our log rules if we wanted to. Like we could bring the 2 up and make that 25 and then divide. I really don't care. It's just a constant. If you leave it like that or if you condense it, it doesn't really matter to me. It doesn't change what you're going to end up with as far as your solution. So now I'm just going to divide to get x by itself. So I have natural log of 2 divided by 2 times the natural log of 5 minus the natural log of 2 equals x. So the only time you have to do anything to simplify the natural log is if your input happens to have an e in it. So if you had the natural log of e, you would call it 1, right? Or if you had the natural log of e to the 5th, you would call it 5. So if it's just the natural log of some other number, you can just leave it alone as a constant and just solve for your x value. Okay. Tonight you have, or over the weekend rather,